So hi students, thanks for joining us today. This is the Pathway seminar, and today we're going to hear from Dr. Sakalis, who's our undergraduate program chair and a faculty member in the controls systems area. And then later you'll hear from Dr. Reislein, who's actually a graduate program chair of the computer engineering program, but a specialist in the signal processing area. So we'll hear from both of them today, and we really appreciate you being here. And we'll start off with Dr. Saklis. So thanks for being here, Dr. Saklis, and we'll let you take it away. And I think you're still on mute, so you can take that off and we'll be able to hear you.
I
Get
thought
there,
that
give me a sec.
Okay, we see your slides.
the host is muting me. Why?
We
You're
can hear you now.
Yeah, you're okay now. Someone
Yep.
must have pressed a button on you. Sorry about that.
Okay. Well, good morning again. And you should be able to see my screen, I guess, the presentation. And I'll start with what's in controls. And usually the first experience with controls comes in 304, in the latter part of 304. We see the feedback and how feedback is becoming a part of technology and what we can do with it, how we do the designs. There is a very extensive tradition that ranges from math to applications, and we'll talk a little bit about some of that and whatever is the new applications. Things that happen today is that feedback becomes cheaper, becomes more intelligent in the sense that we can apply uh, more uh, extended technologies and more elaborate schemes that provide us better performance, better operation capabilities overall. And intelligence, to some extent, is feedback. So this is what we want to discuss. We'll see a little bit of the general formulation. We'll see some of the applications, and then we'll get to the more tangible things that have to do with the curriculum, what kind of courses in the undergraduate program are related to feedback, and potential job opportunities. That's not extensive, that's not all inclusive, but at least some indications of what you should be expecting. Okay, and this is the formulation, the abstraction of the problem. And you can see that in part due to the tradition and the original sources of feedback in the math disciplines, uh, the uh, the entire formulation of the problem is so abstract so that it can be applied to a lot of very different systems. And you can see airplanes, helicopters, etc., which is one of the uh, modern applications where feedback made a lot of difference. Uh, you probably know that a lot of the new high-performance fighter aircraft, they're not stable. So in order to fly, they need to have active feedback control. Otherwise, the pilots themselves cannot fly them like that. Uh, and rocket applications, but also in manufacturing. Um, and then we'll see robotics later on and biomedical applications. So the general formulation is that we have a system, P, or a plant, it's another common name, which we want to control. We want to adjust the inputs, the manipulated variables, things that we can change, so that the outputs or the quantities of interest behave in a certain way. And we do that by measuring these quantities, and that's the part of the feedback. We feed the measurements back to a controller, and the controller decides how to adjust the controls. The problem in the controls is how to design this controller and how to implement it. Typically, modern implementations will involve a computer, which is an extra step in how to describe mixed, discrete, continuous systems. The controller is working in a discrete domain. It's implemented by a computer program. The system is typically a physical system. And the design and the definition of what we try to do is part of the feedback problem. Some common applications here, cruise control. It's one that was happening probably 30 years ago, and the big auto companies that were trying to introduce cruise control in automobiles and cars. And the evolution is that today we are trying to make self-driving cars, where feedback is only part of the problem. The other part is figuring out the environment, figuring out the measurements. The original problem, the speed was something that was relatively easily measured. And now the figuring out where the road is and if there are pedestrians on the road or are there cars, and what we need to do, that requires a lot more information. But still, the fundamental problem remains more or less the same. I mentioned some rockets, and down below there is some robotic applications and lab applications that we can do. That's the nice thing about this type of applications, that we can have test systems relatively inexpensive, where we can test the design techniques. Versus, of course, if you try to apply feedback in a rocket or in a missile, or even in the space shuttle, it's the testing is not so easy and not cheap anymore. Typical issues that we have to deal with, they have to do with the modeling of the systems themselves. A lot of times we have to understand nonlinear dynamics. We have to look at systems which are described either ordinary or partial differential equations. And they may include nonlinearities, which means that their behavior is not analyzed very easily. Things that have to do with unstable systems and time delays, they make the system descriptions and also the constraints of the systems a lot more complicated and a lot more difficult. And the main thing, which is the big objective and the main purpose of feedback, is to deal with uncertainty. So all these things happen, and we know and we understand that we don't really know the system very well. We don't know the inputs to the system very well. There may be additional disturbances in the system. For example, additional forces that act on robotic mechanisms, or drag in cars, and wind gusts in airplanes, and so on. So there is a rich literature about the modeling and the handling of the uncertainty. How do we deal with it? How do we describe specifications that include things like that? And finally, the implementation part. So once we decide what kind of properties we want from the control system, how do we implement them? How do we implement transfer functions? How do we discretize transfer functions, and so on. And one of the big tasks in control systems, and that's part of the heritage of control systems, is how to do it in a systematic way, meaning that we want to be able to handle all these different physical systems using similar tools, using the same basic tools, just change the math to represent the new system. So there is a sequence of how we deal with the different steps, the design process. It's an iterative process, but the main objective is to be able to do these descriptions again in a unified way so that we can handle different problems using the same tools. And the applications are everywhere and in different types of industries. It's mostly, we are talking about a multidisciplinary field because, for one, the plants are usually not part of the control system design, or they're usually defined somewhere. They're part of the other side of the discipline. And the control is aiming to make that system behave more predictably. Okay, and I did mention different types of applications. Acoustic is a part of the of signal processing, and we can see feedback applications in it. Aerospace, I mentioned that was one of the big and successful applications starting in the 50s and the 60s. Manufacturing came a little bit later, especially semiconductor manufacturing, which is a big part of the local economy here. The biological applications, especially in terms of prosthetics, and also what has to do with disease and epidemic containment, drug delivery, and so on. Defense is always a big part of the hiring industry, or at least the driving industry. And one thing to mention here is that there are also applications that have to do with economics and finances, because even that we can think of it as a big system with lots of variables and lots of uncertainty, where we can apply control inputs, where can manipulate certain variables and expect to get a better return on our investments. So there are applications in very different type of domains. Okay, and I'll skip some of that. You can always look at the slides later on. They will be available in case you want to see more details. So what are the courses? The courses that are associated with feedback control. And things are starting with the preliminaries, differential equations, linear algebra. Linear algebra is very fundamental in controls. And that's in part of the numerical applications and in all the computations that we have to do. Signals and systems, of course, that's the math background. 304 is the first class where we see feedback applications, at least get an idea what is the meaning of a design, and with a primary interest in being able to design relatively simple controllers for, let's say, either lab applications or at least some mainstream applications in general. 480, 481 are the senior level courses in undergraduate. 480 is the basic concepts of feedback, continuous time. And it's what we call the classical feedback theory. And 481 is computer control systems, has some theory, but dealing mostly with problems that come up when we try to do the implementation with computers. So discrete time, embedded systems, how the computers work as related to feedback control. And then there is a set of graduate level courses where we see the more elaborate, the more sophisticated algorithms. We see more theory and more techniques, how we can design controllers that do have better performance, that can deal with more complicated systems and so on. Linear systems 582, nonlinear 586, and there's also other supporting material here. Optimal control 587, and neural nets 511, adaptive control 686, which includes some of the adaptation, identification, and control, and how all of these things fit together. And a lot of these are also relevant in terms of robotics, which is one of the big areas nowadays. Other courses, system identification comes from SEMTI. They offer that. We don't offer explicitly system identification except whatever is in adaptive control. And there's always a good recommendation, as far as I'm concerned, to take courses in the math department if you come to that point. Applied optimization and numerical analysis, they're always useful for engineers. I have a note here of what was in the MSc exam, that the format of that has changed. So we evaluate portfolios now. But this shows what are what we consider as the main courses in the controls curriculum. Okay, so it's a few of us, and typically this is the faculty that deals with some level of control problems, not necessarily classical feedback, but different types of applications. And the topics are system modeling, control systems, neural nets, adaptive and learning systems, and the real-time applications. And those are applications where most of us have done at least some work, and we have expertise on that. And again, I put down here in terms of job opportunities, they range in different types of industries, and again, with the idea of multidisciplinary type of applications. My recommendation is always that the good idea is to couple a controls background together with another type of another discipline, and you can fit pretty much all of the other electrical engineering disciplines, power, or robotics, or circuits. You can always mix and match according to preference. Different types of industries who have employed and are employing controls engineers in the past. Okay, and technologies that we see that are related, or at least they have applications from feedback control and optimization and optimal control theory. So I put a list that you can take a look later on at leisure. Okay, and different types of applications. And I'm not going to start listing each one of them separately. And I mentioned that a lot of the current interest is in the robotic systems, hypersonic vehicles, and aerospace, buildings, how you control the different variables that you have in order to minimize energy consumption in buildings, power applications. Of course, the power group has their own versions of control, or at least some control theory, but it's a nice combination of two disciplines in this case. Medical applications, and I mentioned about that. Okay, and then at the end there are some links which can be useful in getting some more ideas of potential industries and applications that you find in terms of the general technology of feedback. Okay, I'll stop my general presentation here, try to take questions.
Yeah, we
So
do
for
have one
80
question here. Oh, sorry, I cut you off. We
Yeah.
do have one question about curriculum. So there, Nathan's asking if there are overlaps between 480 and 481.
There are some overlaps between 480 and 481 in the sense that dealing with the stabilization problem or dealing with PID designs, at least in continuous time, well, there is some theory behind that. So there is overlap, but it's not, there is a lot more which is exclusive to each one of the two. 480 is not a requirement. The prerequisite for both of them, and that's for the logistics and how the classes work, the prerequisite is 203. So you need to have signals and systems. You need to know Fourier Laplace transforms, Z transforms, and that's it. Now, 304 is presenting applications of 203, of the 203 theory, in different fields, different problems. The filtering problem, the sampling and reconstruction problem, feedback and communications problems, and multiplexing. So there will be, let's say, some overlap between 304 and 480 and 481. But again, they're not the same. And none of these is a prerequisite. So the prerequisite is just 203. However, when you do take the systems classes, eventually you have to take 304.
Got it. Thanks for that.
Links. I hope these links are working.
Yeah, we will Stanley, we'll try to get this presentation with the links sent out in a shareable format. We'll work on that.
Yeah,
We don't
just
have that.
make them public somewhere.
Yeah, we'll do that for you. There'll be a little bit of a delay, Stanley, but we'll get that to you. Thanks for asking. Are there other questions for Dr. Sakalis? Great. I think Dr. Reislein is here, so we
All
can
right.
yeah, we can move on to the next one. But thank you, Dr. Sakalis, for your time today. We really appreciate it.
Thank you too.
So students, this is the next part. Once we get this will move on to the signal processing area. So that's there's a lot of connections between the two. That's why we connect them. And as Dr. Sakalis mentioned, some of the controls courses have 203 as a prerequisite, which is the signals class that you'll take, the introductory one. But anyway, this is Dr. Martin Reislein. He's a faculty member in the signals area. He's also program chair of our graduate program in computer engineering, which is great. So thanks, Dr. Reislein, for being here, and go right ahead. Thanks.
Thank you for having me again. Also for computer engineering, this will be presented, I think, in 2 weeks, or is it after spring break then? So it will come up. So we have a special presentation then on the graduate program in computer engineering coming up. Today, I'm wearing the hat of representing signal processing communications, SPCOM. Usually Professor Spanias actually has given these presentations, but he cannot make it today. And Professor Yingcheng Lei is sort of our group leader in signal processing communications, and I'm representing this group today. So yeah, signal processing communications, basic field, subfield in electrical engineering is quite well established. So we have on one hand the processing of signals, and then you see here some representation, autonomous driving, an example. And once these are processed locally, oftentimes these are then transported over communication networks. So the internet essentially is a vehicle for processed signals. And so IEEE network, IEEE communications magazine, you see here are common magazine style publications disseminating research and developments in networking then, and the signal processing magazine is more about the local signal processing. Yes, let's dive into the area a bit more. So signal processing has many applications. Example here is medical signals. If you have an ECG, EKG, or other measurements, medical or machines, they are usually processed in order to make sense of them and to be able to compute and make decisions. Think of data science as a follow-on to signal processing. Aside from medical, there are many other application domains, music, video being a classical application, all the audio, video compression, think also of 3D video, think of the metaverse, immersive environments, augmented reality, virtual reality, extended reality. All those areas have enormous amounts of signals that need to be processed in order to be understood and conveyed. Classic also radar for military, weather applications, DNA, structural health here, and many others. Is all signals that are coming from our outside world in analog form. Usually they need to be digitized and then processed by computers in digital form. So oftentimes it's digital signal processing. On the communication side, you have wireless networks. So these days, more wireless is the predominant way to access the internet, as we all experience every day. Very few people are still wired and tethered to an Ethernet or a coax cable to the internet. We have wireless standards, 3G, 4G, 5G, 6G coming up. These are all based on communications fundamentals that are driving these standards. In this context, also think of expanding horizons with 6G of big systems coming up that range from satellite communication involving terrestrial and satellite components. On the horizon, also machine learning, as you see here, and quantum being as emerging areas. Also, if there are any questions, please jump in or end in the chat, please. We'll keep monitoring that. Any questions so far? No? If that's all good, then we jump maybe forward to networks. So aside from so what is the distinction between communications and networks? Networks traditionally have either 5 or 7 layer architecture, protocol layer architecture, depending on whether you follow the more internet style terminology or the OSI, ITU style of representation. We in the US usually follow the internet styles with 5 layers. On those 5 layers, the very bottom layer is so-called the physical communication layer. And physical communication, the layer 1 or physical layer, is communications. So this deals with the real antennas and propagation and processing coding. So this is communications. And then if you go on top of that, layers 2, 3, 4, 5 deal then with networking. These deals with data link layer, network layer, transport layer, application layer, and there's a lot of terminologies. And these have all different functions to make the internet work. So the internet is a 5-layer architecture. And the bottom layer, the physical layer, is layer 1, is communications. The upper layers 2 to 5 are usually dealt with in networking. So you have here smart grids, all the internet type of architectures, all these services, video streaming, Netflix, all those applications you interact with every day, email, everything you imagine, texting, all that requires all 5 layers to work. So it's very important that all these things come together. Networking ties all these things together. In our school here at Fulton, we also have a collaborative program that bridges from engineering to arts. This is the AME program. So if you have an interest in this, is the Herberger Fine School of Arts, working together with Fulton School of Engineering. There are a few faculty in this group, a subgroup of SPCOM. Speaking of faculty, we have a fairly large group of faculty. Big overviews here. We also have good representations of female professors, highlighted here in blue color. So if you are, we always seek a balance, of course, of gender and other criteria. So there's a very welcoming environment here, and you find also, very importantly, that we have a very fine-grained coverage of topics. If you go to other schools, you have maybe this many faculty in the entire EE field, versus we have essentially an entire department here, if you will, on SPCOM. So we have a very, very fine-grained coverage of every topic. So every topic you can imagine, we have an expert here at ASU in Fulton. So it's a very good place if you want to go on then towards the PhD, potentially even. There's definitely research in every little facet of SPCOM going on here at Fulton at ASU. Speaking of careers, SPCOM branches into many careers that attach to all these signal processing, communications, networking fields. It's kind of laid out here. Traditionally, communications has played a big role, and this ties also into the circuit implementation. So Intel, Qualcomm, Microchip, all these companies need to design not only circuits and CPUs, but the CPU eventually has to put the data, the computed data on the network. So network interfaces are very important. Input, output, I/O is very important. And all the I/O, all the networking coprocessors, all the networking, computing in network is involving knowledge from SPCOM interwoven with computer architecture and circuits. So it all comes together, and SPCOM plays a very important role because most of the data that's computed somewhere has to be done delivered somewhere else in order to get insights, and it's not all in one place. It's a distributed, ubiquitous world, right? So communications is very, very important, and whatever you compute has to be eventually transported over a network. I mentioned some companies. Here's another quick overview. So it's very broad, as you see here, it's communications, military domains, others. So it's a very broad communications, signal processing has good employers here. And as, of course, the strong push in the valley towards circuitry and microelectronics, but the microelectronics also need SPCOM. So there's in SPCOM as well, good opportunities. Speaking of courses, so as you're probably familiar, we have the signal processing sequence going from 203, 304, 350. This is what you may be going through right now. And these then go on and then launch into more detailed senior level courses, digital signal processing, communication systems. So the 455 is physical layer 1 communications. 459 communication networks is then Internet Protocol stack from link layer 2 to layer 5. So layer 1 physical layer is 455. 459 is the layers 2 to 5. So 455 and 459 together cover all layers of the Internet Protocol stack. 404 is more like a kind of a add-on to digital signal processing, giving a bit more hands-on experience and a closer look at some of the real-time aspects. Also, real-time is very important, especially with 5G and 6G communications. The focus is mainly on machine communication, control loops, as you just heard. Timeliness is very important in order to have stable control. Assembly lines, industrial controls, the smart grid, all those require very low latency communications, low latency signal processing. So the push towards low latency is very important. Also for autonomous vehicles, latency is critical. These are some of the graduate level courses that are in SPCOM, and there are more, and they're constantly expanding, courtesy also of various 598 special topics. As you have seen earlier, we have a fairly large group of faculty, and many of our faculty have special topics courses, these 598s that are hitting on very hot topics that are currently just emerging. So it's a good idea to always look for opportunities to branch out in these new topics that are also in high demand, oftentimes by employers looking to get into a particular area. Good. Yeah, and why graduate school? Obviously, in the BS program, so it's very important to have the foundation. However, SPCOM is a very well settled, established area, so it's important to have the base background, but oftentimes the BS is not enough for getting really deep into a more development, front lines of engineering type of profession. So the master's is oftentimes the standard for many of the engineering careers in SPCOM. And beyond that, demand is increasing for PhD level expertise, both in classical academic institutions, universities, but also industry. So all the big ones, Intel, Qualcomm, Microchip, and so on, hire PhD graduates from our SPCOM program. And the very advanced systems that are being developed in these companies do require the PhD level of expertise and PhD level of understanding and reasoning and pushing development forward. Also to point out, we have a very convenient way actually to get into the PhD program. There's a direct PhD, so it does not require a master's first. Rather, you jump directly from the BS undergrad program into the direct PhD to complete the master's coursework and the PhD level coursework and the PhD research all in one shot. And I mean, it's possible to earn the master's and PhD in 4 years. Depending on how research goes, it can be done faster. I've seen some students do it in, if you really push it, 3 years or even 2.5. If you really things go smoothly, if a good topic that goes forward quickly could be done in 3 years or even 2.5. If you really like the record speed. There are fellowships, and usually the PhD research is funded through research assistantships that are administered by the individual faculty members. Yeah, so there's funding support available. That is it. Good. Questions? I hope I wasn't too fast now, but it's good to have time for questions.
No, that wasn't. Thank you for your. I don't see any questions in there now. But students, if you have some, now would be a great time for it. Signal processing is a popular area, and it's not one that a lot of people think of, right? When a lot of undergraduates just think about EE and they focus on the circuits area, but there's a big demand in the signals area too.
And there's a lot of buzz also in the news, popular media about circuits in microelectronics with TSMC, Intel, all those large fabs building the chips. And of course, this is important. This is how all the signal processing is implemented. But this is also important at the same time to have the background in SPCOM. And there's also large demand nowadays for specialized accelerators that are special design circuits for specific SPCOM tasks, and those are also being developed. At the same level with this push, there should be general purpose computing and how to conduct these specialized operations very efficiently on general purpose CPUs, or should you offload to special circuitry, special hardware accelerators, and how do those then integrate efficiently with CPUs? So there's always a back and forth. Yeah.
We do have a question here from Kay. She's asking for the communication networks, would the class talk about software side, like how hardware and software are connected?
Yes. So in EE, so our EE 459 is mostly protocols oriented. So there's no programming assignments. It's a little bit different from traditional EE courses where you calculate Fourier transform and the like. So there's no Fourier transforms, no Laplace transforms. Those are in signal processing, yeah, and in communications as well, in the physical layer. So signal processing communications is classical EE in a sense that it's mass-based transforms, and because this is how the nature, the physics just drive the signals. When you go up then to layer 2, link layer and higher layers, it's more human protocol driven. So there are certain laws, certain protocols, there are certain greetings that the computers have to exchange. And according to those laws and rules, the internet operates then. And so in 459, we study these laws or protocols and behaviors. So it's less hardware or software directly. It's more the rules that govern the behaviors. And these rules are fundamentally, they could be implemented in software or hardware. Oftentimes these days, up to layer 2, 3, it's mostly hardware. And then at layers 3, 4, 5, mostly software, just because of the way the complexity and the flexibility trades off. So it's not really hardware with the software. It's more of understanding the fundamental, what needs to be done and that is separate from how is it done, yeah, in the way that's taught here. I know there are other if you go to say a community college and you get, or you go to Cisco and get Cisco certified, there it's more about how it's done. At the university level, it's more about what needs to be done and why. Yeah, so there's a bit of distinction in the way at the university we approach these fields versus say a technician level view of these fields. You know?
Yeah, this is an
It makes
interesting
sense,
question.
yeah.
Yeah, this is a good question from Stanley here. He's asking if you have any thoughts on how signals applications would play out in sustainable or clean technology.
Yeah, oh, good question, very good question. Yeah, actually very interesting. So Professor Spanias, who mentioned earlier, with some colleagues from SPCom, actually very active nowadays in processing signals from solar plants. So if you have solar, it's very important to orient these panels, and it's also very important to deal in a very smart, rich, judicious way with the generated photovoltaic power because it's so time dependent. So you have to be very smart in processing signals, a lot of signals, to figure out how to orient these panels, when to operate them, and then how to harvest the energy. So a lot of signal processing involved in these modern sustainable energy fields. You know.
Yeah, thanks for that. That's a great couple of good applied questions. I think that may be all for today on questions, but we do appreciate your time, and students, we will work to get these presentations posted so you can review them or anything else. But thank you very much, Dr. Reislein, for giving us your time today.
Thank you. Thank you. Bye-bye.
Thank you.